Okay, maybe it's working now. Let me know if you guys can hear me. Sorry for any hiccups. I think I am live now. I think I am live. Let me go ahead and reload. I should be live now. Can you guys hear me? Can you guys hear me now? I think the stream is going through, but do let me know. And all right, not yet. This is so annoying. I don't know what's going on here. Let's see. I am going to, let me go ahead and I'm going to see if I can get, maybe it's going to a different, maybe it's going through a different link. In fact, how about, I'm going to paste this here. Try that link instead. And let's see if that works. And now when I click on that link, I do. Okay. All right. So I see for some reason it's going to a different link. All right. So people are transferring over. And for some reason, we got to fix this issue because I know it's very annoying. We cannot have good office hours, productive office hours, if people don't know the link. And so I think YouTube might have changed something. So it's making it difficult for us to run these things here. Okay, and I think it's working now. I think it is working. So welcome guys, Worldcon office hours. Sorry for the delay, sorry for the issue, sorry for the trouble, but we are back. And yeah, so thank you for your patience, thank you for your understanding. A couple things that you might have missed when I was talking to no one apparently is we're wrapping up with week 2. I'm going to put something on the agenda. So I'm going to brought up the concept of priority queues and heaps. So I will talk about priority queues and heaps. And from that lesson, we're also going to examine it in terms of time complexity. One of the things we want to build up is we want to build up the skills to be able to look at an algorithm and figure out what is the time complexity. Because this will occur when we go into Unit 2. This will happen when we go on to Unit 2. And Unit 2, which is all about machine learning, heavily focused on machine learning, we will take a crack at these machine learning algorithms, open up their hood and see how they work. And one of the things we need to know for these machine learning algorithms is their time complexity. So we can get a good feel for how long will it take to train those models if we were to increase our training set by the number of rows and the number of columns. So that's the whole thing, how we analyze those time complexities and those algorithms is at Unit 2. But of course in Unit 1, we introduce the concept of time complexity. We'll see some algorithms and get comfortable how to look at and understand their time complexity. And I think looking at priority queues and heaps is a good way to address that. Okay. All right. Let me know anything to throw on the agenda. And I'm going to put the IP mini project. We're getting closer our way to completing that, so we can move on to VC. I see someone is asking about the VC mini project. And I like to do these things in order, but if it's a quick question, I can go ahead and tackle that. So K means I kind of want to do honor the fact that people are showing up for office hours. Someone is saying, did I miss linear regression? And the answer is no, you did not miss linear regression. Linear regression is a topic reserved for Unit 2. Someone is asking about hyperparameter grid search for CNN. And keep in mind, I'll just go ahead and put that on the agenda, decorators, and CNN. It's a very specific question, so maybe I might not get to it. All right, let me know anything to throw on the agenda. Okay, let's see. Like your last lecture on decorators, thank you. Like I said, decorators is, you might not write too many decorators in your life. I've written a couple, but you'll definitely be using them, right? So, and one of the things I like to do for office hours is there's a lot of stuff to learn, right? So I like to use office hours to introduce additional topics, things that are kind of fall into the cracks of the curriculum. Not to knock down our curriculum, but there's a lot to talk about. We do tend to focus on the most important things, but there's just so many important things to learn. So let's go ahead, and with that said, let me know. Someone says, question 3 of the mini project is driving me crazy. All right, so hopefully we can relieve that problem as we go forward. So let me know any additional topics, but I will first talk about priority queues and heaps. Let's talk about that, and then we'll go into the IP mini project and so forth, maybe tackle some of these other ones on our agenda. And like I said, I do honor what people post on the agenda. I may not get to it for today, but I put it on a physical notepad. I have a notepad where I put the agenda so we can make sure that things people bring up, they do get resolved and tackled as we go forth. And I think that's plenty of talking on my behalf. Been talking about 10 minutes. Haven't really done any coding or any explanation, introduce any new topics. So let's go into talk about priority queues and heaps. So what is a queue? Well, a queue is a fancy way of saying a line. I think it's more of a British English, but I could be wrong. I speak American English, but I say a line, but I think they say queue. But regardless, a queue is a data structure that follows this principle that the first one in is the first one out. Just like you're in a line for, I don't know, getting groceries, right? Maybe you're in a line trying to get groceries. Maybe they're trying to limit the number of people in the store, so you queue up, perhaps 2 meters away, 6 feet apart, and they're there, and the first person in the line is the first person that gets serviced. Right? There's a queue. It's a line. If you're the first one there, you're the first one who gets serviced. So we call this FIFO. First one in, first one out. So this right here is a queue. The data structure queue. And this is in contrast to a stack. And a stack is first one in, last one out. And this is a stack. And you can think of why it's called a stack, because you're stacking books. If I stack this book first, and then I stack this book second, and this one third, and I start removing books, the first one that gets removed is the newest one, the first one I introduce. I even call this last one in, first one out. So we have stacking queues. And for these data structures, you can think of this is the idea of this data structure. That's going to have this property, specifically the queue, that the first one in is the first one out. That is the criteria for this data structure. However, there's a way to implement this data structure. This is the idea of a data structure, first one in, first one out. And then we can talk about how we implement this in practice. Any questions right now about what a queue is? Raguraj, thank you for a little more context about your decorators. Okay. Hello, Vera. Now let's take this concept of a queue and let's add more into it. Maybe we want to have a queue, but there's priority involved, where it's not necessarily the first person we service or take care of may not be the first one in. But maybe we have priority, we label priority for the people who are waiting in line. Maybe there is a very important person and they should be the first one to go into the store. right? Maybe not great, but let's go into how we can implement this. And or another example is maybe you have a set of tasks. You have a set of tasks that you have to do, but you're going to prioritize them based upon their priority, how urgent they need to be addressed. You may not want to solve the task as the first one that comes in is the first one you take care of. Maybe a better prioritization is which one has the higher need, the higher urgency. Let's take care of that one first. All right, IP mini projects Q4 and Q5, so I can make sure that is part of the agenda, make our way with Q4 and Q5 of the IP mini project. Okay. So what I could do to implement this queue is I can take an array of values. And then let's say I create my array, and I'm going to put the level of urgency in this array, where a higher number is a higher level of urgency. So for example, I have 4 and 6 and 1, maybe 6 again, and 1 and 1 and 7, 2, 2, and 3. And these here represents the urgency of a task. And I want to do whichever task has the highest urgency. So if I have this as my array, if I want to figure out which task has the highest urgency, what I need to do is I need to go through the entire array and look for which element has the highest priority. So I have to go through each one and see which one has the highest priority. And there it is. I found that one. But notice how to scan through all the elements of the array. So this one has my highest priority. So that means I got to tackle that one first. So that requires me scanning through the entire array. So that to look up or peek is an order n operation. In other words, if I have an array of 10 tasks and I were to double it to 20, it would take me twice as long to find which task has the highest priority, because it involves me going through the entire array and figuring out which one has the highest priority. So if it takes me 5 seconds to do this process and were to double my array, double how many tasks I have, then it will roughly take me 10 seconds. It's a linear correlation. It's a linear time complexity. Hence, order n, where n is the size of my array, the size of my task, in other words, or how many tasks, how many members I have. So lookup and peek is an order n operation. If I want to insert a new task, well, that's an order 1 operation. If I just want to insert a new member, I could just insert at the very end. No need to scan through the entire array. It's independent of the size of my array. This is an order 1 operation. Every time you have an order 1 time complexity, what that means is the task, how long the task take, is independent, is not controlled by the size of your array, how many members you have in your data structure. Because I can just insert a new one at the very end. Insertion is an order 1. In finally removing the task that had the highest priority, removal, this is an order n operation. Someone is asking, is this unit 1 or unit 2? Because the description shows unit 2. Yeah, I think this is messing up with regarding our how we're calling. I think YouTube is messing something up, but sorry about that. I will change the description right here. In fact, I would say, give me a sec, WorldQuant University office hours. This is unit 1, guys. Sorry about that. I think for some reason the thumbnails and descriptions are getting messed up with our other office hours. We have to track this down and fix it. So it's resolved going to the future weeks. But this is unit 1, so sorry for any confusion. I do mention things about unit 2 as a motivation to make sure the things that I'm talking about, I say, hey, this comes going to be important as we move on. So sorry about that. This is unit 1 office hours. Okay. All right, any questions people have about this implementing a priority queue with this array? And why those time complexities are what we talk about. An order n for lookup, an order 1 for insertion, and an order n for removal. Okay, let me know any follow-ups. Before we try to think about a better way to go about doing this. What a double-ended queue? Do you mean a doubly linked list? Okay. All right, can you explain why removal is order n? Yeah, I can explain that right now. I understand why we need it, but not exactly how it works. So let me know exactly what you mean by not knowing exactly how it works. Can you add a little more description on that so I know what you mean by that? And I'll take a look at Joseph's question about, can you explain why remove is order n? Okay. So the removal is order n because when I remove, I want to remove the task with the highest urgency. And these right here, I have the urgency as my task. So what I have to do is I have to go through the entire array to see which one had the highest priority. So if my array is 10 members, I have to go through all 10 of them. And it's removal, and when I say removal, removal of the highest priority. Removal, and I say it's highest, removing highest priority. Let me go ahead and put that right there. Highest priority. How to practically go into the array and what parameters it should look to set the priority. Okay, so we will, so right now we're not writing any code and we're not talking about any Python implementations. We can see how Python would implement this, but right now we're introducing this data structure and we'll see how to best implement it. How do we practically go into the array and look at what parameters? But you can imagine if we were to implement this in Python, we would have to iterate through all the elements. We have to do something like this, in fact. Let's write some code. This is not how you would actually implement it because there's a built-in priority queue in Python, but I can take this data structure and I can say array equals that. And I can say for let's say I val in enumerate array, and I can say set up a max value, max val, set it equal to 0, something like that, and I can say if val is greater than max val, then I say max val equals val, and I int max equals I. And then I can go ahead and say set up my int max to be some sort of default value like 0. And then I look at int max and I can do my array int max and I get 9. So there we go. All right. So this here, if I were to double my array, it would roughly take twice as long. That is why it's a order n time complexity. So this is how you implement it in Python. But we're going to talk about a better way. Python has a built-in way to do priority queues, so we will see that. But hopefully that answers your question. I'm keeping things conceptual at the moment. So a better way to implement this, a priority queue, is using a heap. Let's use a heap. All right, let's talk about what a heap is. So let's talk about a tree. For a heap, we're going to construct a tree. And tree data structures come up a lot. In fact, there's a machine learning model called decision tree. And what a decision tree is a set of questions for you to arrive at some answer. So trees show up a lot through our studies. So what we could do is we could represent this array using a tree structure. And the reason why it's called a tree is because what I'm going to show you here kind of looks like an inverted tree, a tree that's upside down. Okay, so I'm going to draw this tree here. So it's a binary tree, and what that means is that for every node, there are two children. It splits into two, or at most two. So I'm drawing a tree, and what I'm putting here are priority values. Okay, so this right here is my tree. So notice it kind of looks like an upside down tree. This is the root. We have two children, and then for the children, they have two children, and so forth. And when we use priority queue, so an example of using priority queue is maybe you had a set of tasks, and you want to be able to work on the task. The first task you work on is the one with the highest urgency. So maybe an example of using priority queue is you have a set of tasks that need to be done. There's a set of priorities that tell you which one you should tackle first. But as you solve those problems, you solve those tasks, new ones can come in. And you want to make sure that when you finish the most urgent task, the next task you work on is the most urgent one. And we got to find an efficient way to figure out what is the most urgent task we should work on next. Someone is asking me a question about decision trees or logistic regression. This year I am talking about a tree structure, heaps, that represent data in a tree structure which is analogous to decision trees. We're not talking about ML here. By the way, this is Unit 1. There might have been some confusion about what unit office hours this is. This is Unit 1 office hours. But if you're Unit 2, you're more than welcome to stay. But we're talking about representing a priority queue using a tree structure. And the other thing we've done here is that the element with the highest priority is at the very top, at the very root of the tree. And its children, when we construct this tree, has to be less than the parent. So we have 35 here, and its children are less than 35. We have 26, and its children are 15 and 24. They are less than 26. So now my question to you is, if I arrange my tasks priorities using this tree structure, how long would it take to look up the urgency, the task with the greatest urgency? how long would it take to look up the most urgent task? In terms of how many tasks I have, consider that. Minimum, right? It's very quick, right? I agree with minimum. Can we throw a time complexity on it? Can you describe to me in terms of how many tasks I have, how long would it take to figure out the task with the most urgency? The highest urgency is always at the top, right? So if it's always at the top, then that means that it doesn't matter how many tasks I have. If I arrange my task in this tree structure so that the task with the greatest priority is at the top, the greatest urgency, then for me to look up and figure out which task has the highest urgency is unaffected by how big my tree is. It's always at the top. It's always at the root. And every time I'm analyzing algorithms and the time to do something is independent of how many members I have, that means it's an order 1 operation. So yes, CB, it's an order 1 operation. So that means lookup is order 1. I really messed up lookup right there. This is already an improvement. Before we talked about a simple array to implement a priority queue. The time to look up the most urgent task was order n. So if we were to double the number of tasks, it will double the lookup time. But now it's independent of size. So we've got improvement. All right, someone is asking about a video list, a video link for this, for Unit 1 office hours. I can just put that in the chat, no problem. There it is. There's a playlist for Unit 1. So this is applicable to both stacks and queues. So this here is we are going to do this with the actual implementation is done with the stack. But you could think what I'm trying to show you here is a little more abstract. We're not writing any code at the moment, but we're trying to represent our data in a more efficient way. We're going to figure out what's a good data structure for this concept of priority queues. And the actual way you would implement this in Python is using a list. So someone would say, don't we actually need to construct the heap? Is the construction of the heap less than order n? So the construction of the heap, so you bring up a good point. The construction, I haven't talked about how long it would take to construct this data structure, and construction is order n. So you are right, construction. I kind of glossed over this. Construction is order n. However, we only construct once. We only construct for the first time. And afterwards, we're going to have a very favorable time complexity. So yes, you have to do some, I kind of glossed over this, but the time it takes to construct this data structure as a tree in this format is order n. However, you won't be constructing this data structure every time you're going to add a new member or remove. In fact, we'll talk about insertion and removal just in a bit. But you bring a good point, so thank you for keeping me honest there. All right. Now, let's see what happens if I'm going to insert a new member to this tree. Insertion. Let's see what the time complexity for insertion is. So the beauty of this tree here is that every time I insert a new member, I'm going to modify my tree so that this principle still holds true, that the parent has a greater urgency than its children. So I'm going to insert a new member. Go ahead and do that right now. I'm going to insert, I don't know, let's see, I will insert, what should I insert? I'm going to insert a value of 33. I already did that. I already added 33. I'm going to add 17. How about that? I'm going to add 17. So the way I add it is I add them left to right. So that I add, so this is filled up, that's filled up, filled up, filled up, filled up, filled up. This one doesn't have any children, so I add it right there. But now I'm going to modify this tree so I adhere to this principle that the parents are always greater than the children. So what I'm going to do here is, since 17 is greater than 4, what that means, I need to swap their position. So I'm going to bring this up. I'm going to bring this down. So what I'm saying is, wrong to say the root node has the highest information gain. Information gain is something of interest for decision trees, but we're not using decision trees. We're using trees, but we're not using these trees to make decisions or arrive at answers. So we're not concerned about any information gain here. So if we were to swap these two, if 17 were here and 4 were there, then our tree still has this core property that the parents have a higher priority than the kids. So here, this only took one move. But let's consider the worst case scenario, where I insert a new member, let's say 40. So that means I have to swap here. 40's here. Oh, 40 is still greater than 34. So then I swap. And then I have to swap once more. So the worst case scenario, I will have to traverse this tree all the way to the root. That's the worst case scenario. However, how many swaps would it take in the worst case scenario? If I have a depth of, let's say, D of my tree, in other words, how many layers I have, how many swaps do I have to perform? The depth of the tree minus 1, right? So the depth of the tree. So the swaps, how many swaps I have to perform, is the depth of the tree. And here I have a depth of 1, 2, and 3. So at the most 3 swaps. So there is to figure out the depth of the tree based upon the number of elements in the tree. So the depth of the tree is equal to log base 2 of n. I think there's a plus 1. At most, from minimum of log of n2 all the way to, at most, log of n plus 1. So basically log base 2 of n. So in other words, at worst case scenario, the number of swaps I have to take is the log of n. So if I have, what this means is that if I have about 1,000 members, then the number of swaps at worst is log base 1,000. And And remember, this is log base 2, which comes out to about 10. So the insertion time complexity is order n. Insertion is order n. Sorry, order log n. Sorry, oops, misspoke there. Order log n. And I won't go into this, but removal works just as fine. Removal is a very similar process. It's log n. So while it takes order n to construct, the power behind this heap, is called a heap, a priority heap, is that insertion, removal, or log n processes. And every time you're working with trees, you're going to see a lot of this log n. Because it's a way to get at the number of our depth of our tree. We'll see this when we talk about decision trees unit 2. We'll talk about the time complexity to train and make predictions of our decision trees. And we'll see this log n appear time and time again. And this sure beats what we had before. Removal is order n. And now removal is log n. Lookup is order 1. So let me know any follow-ups. I do want to transition. I do want to spend some time talking about how you would do this in Python, right? We saw the concept. How do we do this in Python? But I think what I'll do is I'll take some questions right now, but then I'll save that for a future office hours because I do want to spend time working through the IP mini project. I like to balance in office hours, some sort of mini lecture and mini project. I like to balance those two things. Any questions right now about this heap? This is called a heap, a priority heap. We also saw a way how we can analyze these algorithms. Okay, I'm going to go and switch gears, but do let me know if there's any follow-ups. Let's make our way through the IP mini project. And someone did ask about exercise 3, and what I'll do is keep in mind that we have a playlist of all past office hours, and I talked about how to tackle Q3. So just out of interest of not repeating myself, I would do recommend that you look at that video. In fact, we have thumbnails you can easily navigate which is the appropriate video. So if you have a question on Q3, take a look at the video I did, I believe, yesterday that goes into our approach for Q3. So with that said, we'll talk about Q4 and maybe we'll make our way to Q5. All right, so we got to optimize how we figure out prime numbers. And one of the shortcuts we will take is if I want to figure out whether, I don't know, the number, I'm going to choose the number 121. If I want to know if this number is prime, earlier what I did is I check if I can divide by 2, divide by 3, divide by 4, divide by 5, all the way to divide by 120. That was my previous approach. So in other words, if I want to check if 121 is prime, at the worst case, I have to do 120 checks. So if I want to check if 1,000 is prime, then at most, maybe not get to it, but at most I'd check order n times. 1,001, I think that's prime, I don't know, but potentially I would have to check 1,000 times. And that's not such a great time complexity. Order n isn't such a great time complexity. But one of the things we realize is in this approach here, we're going to do some redundant checks. all we have to do is check up to the square root of the number. So if we want to check if 121 is prime, we're going to divide by 2, by 3, by 4, by 5, all the way to the square root of 121. The integer, the nearest integer of the square root of 121, which is 11 in this case. So this is a better approach. So now, at worst, what do you think my time complexity is going to be? At worst. And every time we talk about time complexities, sometimes it's good to look at the worst case scenario. That's sort of our ceiling. So what are your thoughts? What is the worst case time complexity here? 1001 is not prime, is someone saying. All right, thank you. So not quite n over 2. Not quite n over 2. Thank you for letting me know that 1001 isn't prime. But you can imagine some very large number that potentially is prime. Someone is asking, will I continue on to Unit 2? I don't know. It depends. It depends what my schedule is, whether I'll do office hours for Unit 2 and next time around. Who knows? I cannot guarantee anything at the moment. So this time complexity will be order square root of n. And oftentimes we ignore someone saying square root of n minus 2. And for simplicity, we like to say the square root of n. Because if n is such a large number, then subtracting 2 isn't going to really change much. So we can be very precise and say square root of n, but we can just say square root of n. Yeah, so this is great. So we can go from maybe checking 1,000 numbers to checking only square root of 100 of 1,000, which I think is about 30. So this is a better approach, a smarter approach. So let's go ahead and implement this. Let me know if there's any questions, but let's go ahead and implement this in Python. I'll go and look at the chat. I already got it set up for you. Let's set up a function called isPrimesFast. So what we'll need to do here is we will need to, I'll put a little doc string here, is iterate from 2 to the square root of our number and return false once we find a number we can evenly divide by. So once we find a case where a number is evenly divisible, then we can just return false. Find that counterexample and return false. All right, thank you for letting me know the divisors of 1001. It was just, hey, it was my best guess of what a very large prime number is. Okay, so let's try this out. So one of the things to keep in mind is that we have these special cases where 2 is a prime number, that special case. So let's go and hard code that. Let's go and hard code that in. So if number is less than 2, in other words 0 or 1, we return, let's return false. And if our number is equal to 2, we will return true. Let's consider those cases there, and now we're going to do our iteration. We're going to iterate through 2 all the way to the square root of the number. So for example, if I want to check if 1001 is prime, then I'm going to iterate from 2 all the way, put a comment here, 2, to square root of 1001. But I want the integer, the nearest integer of the square root of 1001. In other words, I take 1001 and I take the square root, I have to go through 32. So check from 2 all the way to 32. And this here isn't an integer, but one thing I could do is pass it to the integer constructor. So this forces the output to be an integer. So now what I can do is I can use range from 2 all the way to the integer of the number, in this case 1001, square root, raised to the 0.5 power. And I want to include 32, so I will do plus 1. Keep in mind, this is inclusive, exclusive. All right, let me know if you guys have any follow-ups right now.
And I had it for, and I used it for a lesson where you get it, and it didn't even stretch out. It just exploded. Do you know where it is? Yes.
All right, someone says makes sense to them. Anyone else have any follow-ups here?
Doesn't mean I didn't. I just don't remember the
So no need to check from 2 all the way to n. We're checking 2 all the way to the square root of n.
Wait 1 minute. I have to. I can't talk in here. Just a minute. Forgot.
All right, so we can say for p, or say for divisor. Let's be a little more descriptive. For divisor, in range of p of our number, to the integer of that number raised to the 0.5 power, which is a way to take the square root. We do import math, but I like to do the star 0.5. I find that a little easier to do. Plus 1. And we'll check. If we take our number and we were divided by our divisor, and that just so happens to be even, so there is no remainder evenly divisible by our divisor, then that means, hey, we figured out it is not a prime. So we will short circuit the execution and return false. Once we find that counterexample, there is no need to check any further. So we return false. And if we go through all the divisors for a number and we couldn't find a number from 2 to the square root of n that's evenly divisible, well, hell, we have found a prime number. So we will return true. Questions about this function here? Let me know if you have any questions. While you post some stuff in the chat, I'm going to go ahead and run this here. I get an insertion error, so I must have made a mistake here. Must have made a mistake. That's what happens when you live code. So let's see if I can figure out my mistake. All right, for if number is less than 2, return false. If the number is equal to true, 2, we return true. And for divisor in range of, 2, there was my mistake right there. I want to go from 2 always to the square root of the number. Made a little mistake there. And let's try that out. Let me know if there are any questions in the chat. All right, so I see some questions here, so let's go ahead and examine that. I say, why is the return indented in line with the for? So you're talking about this return statement right there, RW? Okay. All right, so this for line here is we are checking if we can divide we're checking all divisors from the number from 2 to the square root of our number. And the whole point here is I don't have to check all the ways. Going back to our discussion what we had before. if I want to check if the number 1001 is prime, I don't have to check from 2, 3, 4, 5 all the way to 1000. What I do is I go all the way up to the square root of 1001. Because afterwards, I'm doing redundant checks. So what I want to do is, for example, if I want to check if the number 1001 is prime, what I need to do is I need to check whether I can evenly divide it by 2, 3, 4, all the way to 32. And why 32? Because 32 is the square root of 1000, is the integer of the square root of 1001 plus 1. So that's what that number star 0.5 means. I do that right there. So for example, if I want to check if 1001 is prime, I check 2, 3, 4, 5 all the way to 32. And star 0.5 means square root. I'm taking a number to the 0.5 power. That's the same thing as taking the square root. So in Python, I can take the square root of a number. Let's say I want to take the square root of 5. I can do star 0.5. Or if I import the math module, I can say math square root of 5. Same thing, no difference. I find this easier to implement because I don't have to import math. In order to do this, I need to import math. So make sure you import math. So this here is checking all the divisors, all my checks. And I'm exploring the fact that I don't have to go from the number 2 all the way to the number. I can stop at the square root of the number. All right. All right, someone is asking about the return line. So here is the reason why the return is indented with respect to the if is because if I just happen to find a number that's evenly divisible, then that means that it's not prime. So there's no need to check all the other numbers. And once I reach a return line in a function, that's it. I return. I am done. I could go through all of them and then finally return. But if I find a case where it is evenly divisible, I'm just going to return false. No need to check any further. And if I go through all the divisors and I didn't return at all, I didn't return in this for loop, that means I tried all the possible divisors. I couldn't find any of them that's evenly divisible. So that means it has to be prime. So I return true instead. So now, at worst, my time complexity is square root of n. At worst. Because maybe I might find a case where it's evenly divisible, and I can just short circuit it. So now I can check this out, and sure enough, I ran this insertion. So that means my is prime, my is prime fast get the same answer, at least for the several test cases I try out. Let's use a time it magic. So this is Jupyter Notebook magic that's going to time the execution, and we should expect this to be significantly faster. Let's run the is prime, the slow version. And we should expect that it should be significantly faster because now the time complexity is square root of n. Someone said, a little off topic, but can you please explain merge, sort, bubble sort, insertion? So I can go and put that in the agenda. Merge, sort, bubble sort, all those nice sorts. How about that? Put that on the agenda. It's still running. It's a rather slow process. Okay, so it took about 5 seconds. So let's see, if it took about 5 seconds for this number here, let's see if we can estimate how long it should take. Before we run this, let's estimate it, right? So if it means, let's see if we can do some simple math here. So if it took, let's say an order n took 5.45 seconds, whatever number, and then if we were to, let's see, it should be, just do my ratios. Man, I'm getting a little blurry here. Sorry about that. This should be, if it took, actually, we can take this and let's divide by 2. I'm going to put this in a new cell. We do this here and divide by 2. This should roughly take half as fast, half the time. If we say it's an order n time complexity. About 100 microseconds, so that isn't true. Yeah, that goes against my point. Oh well. Let's just run this is prime fast. And that took 600 microseconds. So that was simply faster compared to 5 seconds. Okay. So now we're ready for our get primes fast function. So now here we do list comprehensions. We can say, all right, for number in range of all the way to end, let's check if it's prime. So we use the is prime fast, pass the number, and have number there. So basically, same function we had before, the get primes function, list comprehensions from number all the way to range of n, but instead of using our is prime function, we're going to use our is primes fast function. Now we've defined that, the next thing we do is we pass it to the grader, and hopefully we get a score of 1. So the grader will use our function to test it out. Let me know if there are any follow-ups. It looks like we're near the end of our hour, so we won't get to Q5, but it will be on top of our queue, our top priority, if I can make that pun, make that reference to earlier in this lesson of what we should tackle on Monday of next week. But let me know if there are any follow-ups, and I will keep track of this agenda. So I'm going to talk about the decorators and CNN. So let me go ahead and copy paste what they said earlier so I can give a better answer. Someone said where the get primes fast, we had to code that up. The get primes fast, we had to create that. However, it's pretty much exactly our previous get primes. Where it was, forgot where, all the way up, not even there, get primes. It's pretty much the same thing. However, instead of using is prime, we rely on our created is prime fast function. It's the only difference. And I believe this was in one of the notebooks. I forget which one, but we do talk. I think we do introduce this function. I believe if I go here, it might be in our algorithms notebook, I believe. Maybe it's in program flow. Yeah, there was the original one, is prime, and then you were asked to write the get primes function in this mini project. All right, let me know any quick questions people have. We are at our end of our office hours. Didn't get to Q5, but that will be at our top priority on Monday. thank you, Naya, letting us know what's in program flow. With that said, guys, take care. Have a good rest of your day. Have a good Friday and weekend. And we will see you next week. All right, thank you, guys. Take care. And hopefully we have less technical issues moving forward. Take care, guys. And see you next week.